Hello, everyone. Today, we are going to talk about linear differential equation, nth order, part 1. I'm planning to do several parts about it. So today is part 1. Then we see how many parts we can finish the whole linear differential equation nth order, okay? Perhaps at least 3, maybe 4, okay? So at least today is part 1. Okay, then we start. A general form of so-called linear differential equation of n order can be written as anx y prime n plus n minus 1x y prime minus 1 n minus 1 plus a1x y prime plus a0x y equals fx, okay? Here, all the anx, an minus 1x, and a0x are functions of x, okay? The fx is a non-homogeneous term. Here, how to solve this question? The step 1, we say we solve the homogeneous question associated with the original function. We can written as the left side is the same, and the right side fx equals 0. Okay, and how to solve the question? There will be 2 main cases with constant coefficients and with variable coefficients. Then today we are going to talk about with constant coefficients the way. Okay, if the an minus 1x, all the coefficients are, all of them are constant, then here a0 are constant, then we can solve the characteristic equation of original this homogeneous equation. Okay, the characteristic equation can be written as Rn plus n minus 1 Rn minus 1 plus a0 equals 0. For the solutions, we say they are depending on the roots R, okay, the type of the root. First, we can say if all the roots are distinct real roots, R1, R2, they are independent, not equal, okay? Then YH is a homogeneous solution. Sorry. Can be expressed C1 ER1X plus C2 ER2X plus CN ERMX, okay? Then we have the case of repeated roots, R1, okay? Double, triple, multiple roots of R1. Then we can written as ER1X. YH can be written C1 plus C2X plus CMXM minus 1. Okay. Then until n. Okay. M usually is smaller than, m. Okay. If it equals n, we can written as this form. If m smaller than n, most of the case, then we can plus the r n plus 1, we can write the r1, r2 until the rest of the n minus m plus 1, okay? The rest of still can be written RH, okay? The complex alpha plus minus can be written, roots alpha can be written WHE alpha x C1 plus C2, okay? Then we can put them together, okay? If the all the roots, okay? For the variable coefficients, we do next time, okay? Okay, then let's deal with the particular solution, YP. First, we got homogeneous solution, YH. Then we are looking for particular solution, YP. For the non-homogeneous equation ANXYN plus ANXY equals fx, we found the YP using method of undetermined coefficients, okay? If fx is a polynomial, exponential, sine, cosine, then we can assume YP of a similar form. If YP overlaps with YH, we multiply by X, okay? Also, we have another way to deal with this equation. We use so-called variations of parameters. Variation of parameters, okay? In this way, we for any fx, this way is working. For any fx, this is working. But we need to solving some integrals in the steps of solving this problem. Okay. We can express yp as yp equals u1 y1 u2 y2 plus un yn. Okay. Then y1 yn are solutions to the homogeneous equation. Okay. Then the final general solution we can use homogeneous solution plus special the particular solution, 这个 general solution. Let's go through a real case, okay? Example. 3 prime y minus 6y double prime plus 11 y prime minus 6y equals e to x, okay? First, we found the characteristic equation of original one, which can be written as R3 minus 6R squared plus 11R minus 6 equals 0, okay? Then, after factoring, we can find this a case of the real roots, okay? Then, the homogeneous solution YH can be expressed as C1EX plus C2E2X plus C3E3X. Okay, then because this fx is formed as exponential functions, right? And also e2x appears in YH, so we can use overlap. We can use yp equals ax e2x form, okay? Then we do first, second, third differential of this yp, then simplify them, then notifying a factor a e to x, we solve for this a. Then it just easiest simple calculation, we get a equals 1 over 2. So yp is 1 over 2x e 2x. Then the general solution is y, this is equals yh plus yp. Today we are introduce another way of solving nth order linear differential equation use variation of parameters. To solve this one, we try to find the particular solution yp. How to do yp? First, we use the same way to find the y1, y2, yn, the yh, okay? And then we found them, okay? All these yh are called fundamental solutions, y1, y2, yn, okay? Then we express yp as u1, y1, u2, y plus un, yn, okay? Then u1, y2, un are functions to be determined. Then we introduce Walensky system, Walensky matrix, which can be used to find the u1 prime, u2 prime, and un prime, okay? So let's see, u1 prime equals w1 divided by w, okay? The w is all the fundamental solutions of the homogeneous equation, then differential until n minus 1. This is w, okay? Then wi, if this is w, okay? w1, we use this to equals the first column. w1 is the first column. We put w1 here. So w1 equals 0, 0, fx. Here is the same. Then we can use u1 prime equals w1 divided by w. By this way, we can solve all the ui, okay? Then all the ui can be integrated. Then we substitute the ui back into yp, we get a yp. Then the general solution is equal yp plus yh, okay? Now let's see a solution of y double prime minus 3 y prime plus 2y equal x, okay? So the characteristics equation for this homogeneous equation can be expressed r minus 1 times I minus 2 equals 0. So yh can be expressed as c1ex plus c2e2x. So this is can be it's y1, this is y2. Okay. So yp can be expressed u1 y1 plus u2 y2. Okay. So w is y1, then y1 prime, okay, equals e 3x. Then we see this is w1, we put 0 fx into the first column. For the u2, for the w2, we put 0x into the second column. So in this way, we can solve u1 prime and u2 prime. The calculation shows u1 prime equals minus 1. This is 0 minus e3x W is 3x, okay? W, can we see W? W is this times minus this times is 3x, okay? So then we do integrate u1 prime, u2 prime, which equals y minus x minus e minus x respectively, okay? This is the easy part. Then we construct yp. Yp equals u1 y1 plus u2 y2, okay? Then the general solution will be y plus yh plus yp, okay? Now we finish all the part of today's discussions. Next time, I'm going to give more examples. Until next time, thank you for everyone. Bye-bye.